Okay, so this is the start of Unit 7, where we'll be studying thermodynamics and thermochemistry and all about energy of reactions. So, what is energy? Well, energy, as you probably learned from physics, is the capacity to do some sort of work. And in the case of chemistry, when we look at that, we're actually looking at the ability of a reaction to produce or absorb heat from the surroundings. Important that you know the law of conservation of energy. This guy right here. Law of conservation of energy says that total energy of the universe is constant. Super important. First law. Heat involves a transfer of energy between two objects due to temperature differences. So we have known that in the past as enthalpy or delta H. And we're going to study the heck out of enthalpy this unit. We're also going to take a look at today work. Our chemical systems can actually do work, and we'll focus on that. But one of the most important concepts is the idea that enthalpy, as well as entropy and free energy, are something called state functions. A state function is a property that does not depend in any way on the system's past or future. It only depends on present state, meaning we have multiple ways that we can solve for these things. And so part of what this unit is us focusing on how we can solve for delta H, delta S, and delta G, depending upon the kind of data or information we're given. So, chemical energy. Let's start with talking about what the system is and what the surroundings is, because you really do need to be able to differentiate the two. The system in our world, in our chemistry world, is always the reaction. The reaction that's happening is the system. And then the surroundings is everything else. We already know, and this is kind of a review, that an endothermic reaction, heat flows into the system, and we know that means delta H is positive, and the trick to that is endo starts with an EN, and enter starts with an EN. And then exothermic, you know, energy flows out of the system, so our delta H, our enthalpy sign is negative, or our Q, heat, is negative. Exo, exit. And then, again, we've looked at these diagrams quite a few times in both years of chemistry already. These are our potential energy diagrams. This first one, our reactant energy, is much higher than our product energy. Where did the heat go? It exited, so this is definitely an exothermic diagram. And then here, our reactants energy are lower than our product energy. So how did those products get that energy they needed? Heat entered to give them that extra energy, and that was endo. So again, be familiar with those. So now we're going to focus on thinking about things from the perspective of the system and the surroundings, and we will determine our enthalpy by knowing the direction the heat is going. And again, we're looking from the perspective of the system, which is the reaction. So this first question says, is the freezing of water an endothermic or exothermic process? Explain. All right, so when water freezes, it's going from liquid to solid. When it goes from liquid to solid, what happens to the energy? The energy had to leave in order to make those molecules slow down and make our little solid latticey thing known as ice. So if energy is leaving, we call that exothermic. So this is an exothermic process. A lot of people will get confused with that and like, when you freeze stuff, it's cold. Well, what you're doing when you put water into the freezer is you're drawing out the heat. So the heat is leaving the liquid, slowing down the molecules, making it turn to solid. So that is an exothermic process. So we're going to go through and classify each process as exothermic or endothermic. Explain. The system is underlined in each example. So here, your hand is the system, and if it gets cold when you touch ice, if the hand is the system, what is happening? Well, cold is not going into your hand. We look at movement of heat. Heat is actually exiting, so this is exothermic. The ice gets warmer when you touch it. So if your hand was exothermic, the ice was getting warmer. The ice, as the system, is absorbing that heat your hand gave off, so that is endothermic. Water boils in a kettle being heated on the stove. All right, so water is boiling, so that water is absorbing heat from liquid phase to gas phase, and it's absorbing heat that's provided by the stove. So it's weird to think about, but boiling is endothermic. Water vapor condenses on a cold pipe. Well, water vapor, gas, loses energy to become liquid, and that is exothermic. Ice cream melts. What happens with the heat? The system is the ice cream. Endothermic, because the heat goes into the ice cream and melts it. Okay, so now, next part. For each of the following, define a system and its surroundings and give the direction of energy transfer. So in the first example, methane is your system, and methane will react with the oxygen provided by the Bunsen burner. So the Bunsen burner is your surroundings, and the Bunsen burner is giving oxygen, ultimately, to the methane. So the methane is combusting, and we all know that when anything combusts, we have some sort of exothermic reaction. So even though we have a flame and it's hot, additional heat is being released when that methane combusts. Next, we have water drops. Water droplets are the system, and they're sitting on your skin, and your skin is the surrounding. So that water is going to evaporate, and this is the whole reason we sweat physiologically, because it's cooling our body, because that water is going to absorb endothermically the heat from our body and evaporate away, and that's a cooling process for our body. So the water is endothermic. The heat from the surrounding, our skin, enters the water and makes it evaporate. So in addition to knowing about energy and the law of conservation of energy, it's important for us to understand that when we express energy values, there are two parts we have to focus on. We care about the number. We care about the number of kilojoules and joules, so the number is definitely important. But what's even more important than the number is the sign. The sign indicates the direction that either the heat or the entropy or the free energy is going, whether we're leaving the system, whether we're entering the system back and forth. Our sign is just as important. So you can't be sign lazy. No laziness. If you're asked to talk about the number of kilojoules of heat that is released, you have to put a negative in front of that value. That is exothermic. So students will argue, well, it said released, so they know it's, negative. I don't have to put it there. Yeah, you do. No matter what, you always have to have a sign indicating whether something is endo or exothermic, or whether entropy is increasing or decreasing. The sign is crucial. All right, something that's not covered in a great quantity on the AP is something called internal energy. I'm going to go over it because it might show up in a couple multiple choice questions here or there, and I definitely think it'll help you with your work in physics. So you're going to go ahead and have to know the formula that internal energy is equal to the amount of energy or heat produced or used in the system, that's Q, plus work. So, what is work, you ask? Well, we'll talk about that because that's going to be a little bit of a new concept this year for you. Again, probably for the 8 billionth time, we're going to talk about heat. And instead of using enthalpy, we just in this first portion call heat Q. And like you already know, if it's endothermic, the Q is positive. If it's exothermic, the Q or the heat is negative. We use a lowercase q in chemistry, not a capital Q like they do in physics. So what is work? There is only one way that a chemical reaction can do work, and that is by producing a gas and pushing against the environment. So let's say I have a little test tube here, and I am going to have magnesium and hydrochloric acid mixed in my test tube. And just to capture the gas, I'm going to put a little balloon. When I start that reaction, we know that it's a single replacement reaction, and we're going to produce hydrogen gas. In order for the hydrogen gas to fill up this balloon, it's going to have to push against the pressure of the atmosphere. That system is doing work. By the producing gas is the only way a chemical system can do work. So that's what we're going to focus on when we're thinking about reactions that potentially have a negative work. And so you do have to know the signs of work, and the system is our reaction, and the surroundings is the outside atmosphere. I have a little hint, a little way to remember this, which I think will be helpful. Let's say that you are the system, and I'm telling you to do some work. The system does work on the surroundings. So you are the system, you do work. Do you like to do work? No, you don't like to do work. So you think work is negative. So when the system does work on the surroundings, the sign is negative. And this works in physics too, so you can use this later when you get to that. If surroundings does work on the system, let's pretend you're the system and the surroundings may be a plastic surgeon. Well, hey, this plastic surgeon is going to make you look like Angelina Jolie or Brad Pitt. That is positive. So if the surroundings does work on the system, negative, the W is positive. So again, when the system does work, bad, that's negative. When work is done on the system, positive. So again, this is a little bit of a representation of a system doing work. We can see here we have our reaction, and as that reaction does work, it pushes against the atmosphere. We increase in our volume. And that's what we're going to be looking at, is the change in volume. Because when we produce gas, the volume changes as the gas is produced out of the reaction. So you do need to know this equation. This is also going to save you in physics. Work is negative P delta V, where P is going to be our pressure and delta V is going to be our change in volume, where it's the final volume minus initial, just like all other deltas are. And then when you use this and you put atmospheres in for pressure, you get an atmosphere liter, which isn't a really useful unit. So the conversion from liter atmospheres to joules is listed. So there's 101.3 joules per liter atmosphere. And they're usually going to ask you for your answer in joules or kilojoules. So this is going to be a very useful conversion. So let's go ahead and use that negative P delta V equation to solve for the work in these two problems. The question is, which of the following performs more work? So we're going to use work is equal to negative P delta V. So my negative P is negative 2 atmospheres. My change in volume is final minus initial liters. So my answer here is, oops, I already made a mistake. Gosh, I'm so good. It's 4 minus 1, because that would be 1 liter initially. So final 4 liters minus initial 1. That'll give us a 3. So that comes out to be negative 6 liter atmospheres. We don't need to change it to joules because, again, the point is just to compare A and B, which one is going to do more work. So the fact it's negative is good. We know that if we get a negative number, that means the system's doing work. So we did that right. So let's check the next one. Work is equal to, we have this time pressure of 3 atmospheres and we're going from 3, from 1 to 3, so it's final minus initial, 3 minus 1. Oh, looky there, that also gives us 6 liter atmospheres. So it looks like these guys are doing the same amount of work. Nobody is doing more. So that was a trick question, I guess. All right, determine the sign of delta E for each reaction of the following with the listed conditions. So this says an endothermic process that performs work. So I'm going to focus on that. Remember the internal energy equation? So looking at this, I want to know which is true for an endothermic process. Endothermic means we have a positive Q, right? And then that performs work, negative. So let's see which is what in each case. If work is greater than heat, I have more negative than positive, right? If work is greater than heat, I have more negative than positive. So what does that make the sign of my delta E? It makes it negative. Okay, if work is less than heat, I have less negative than positive or more positive than negative. So that makes it delta E positive. All right, so now let's go ahead and do the same thing. We have different conditions though. So for this next example, we're going to do the same setup, but our conditions are a little bit different. We have our delta E equal to, this time this is an exothermic process, so our Q is negative, plus work being done on the system. Yay, plastic surgery, positive. Please don't go home and, tell your parents I'm saying plastic surgery is awesome. I don't think so at all. It's just a metaphor to help you remember something. So let's not be so literal. Anyway, so looking at this first example where we're going to calculate the sign of delta E if work is greater than heat. Well, if we have a greater work, it means our final E will be positive. So this first one is positive. And if we have a work less than heat where we have more Q, that means our delta E will be negative. And that is that. Okay, so we're going to do some math problems now with our two equations. The first question says, calculate the internal energy for a system undergoing an endothermic process in which 15.6 kilojoules of heat flows and where 1.4 kilojoules of work is done on the system. So we know that means work is positive because work is done on the system, and it's endothermic, so that guy has to be positive. Knowing that, we can take both of those and stick it into our equation. Well, they're both positive, so 15.6 kilojoules added to 1.4 kilojoules gives me 17.0 kilojoules. And that's correct. And the sig figs are going to be based on its addition, right? So remember, we round to the least number of decimal places, and both those numbers have one decimal place, so our final answer should have one decimal place. Yay, that was an easy problem. All right, the next one says, calculate the work associated with the expansion of a gas. So where a gas is being produced and it is expanding against the environment. So that means that the system is doing work. So we better get a negative work when we do this problem. And it's calculating it at a constant external pressure of 15 atmospheres. So work, we know, is equal to negative P delta V. So I'm solving for work. Let's see, and my negative P is 15 atm. My final volume is 64 liters. My initial volume is 46 liters. When I do the magic math really quickly, because I already did it ahead of time, I get negative 270 liter atmospheres. So that is calculated work. It came out negative, which means we did it right. I don't need to convert this liter atmospheres to joules. because it didn't tell me to. It's only in the problem like the next problem where we will have to take something like that into account. So let's look at it. Here we go. A balloon is being inflated to its full extent by heating the air inside it. In the final stages of this process, the volume of the balloon changes from 4e6 to 4.5 by the addition, do you see that? Addition of energy. So we know that work's going to have to be negative because we are producing heat, and we also know this is an endothermic process. They want us to calculate delta E. So this is going to require a couple steps. Ultimately, we want to find delta E, right? So delta E, whoa, I need to change that. I don't want a stinking highlighter, I want a stinking pen. Let me get a pen out. Okay, delta E is equal to Q plus W. Well, is there anything we know? Yeah, we know Q. And we know that Q is 1.3, I'm just going to do E to save space, E to the 8 joules. Awesome. So now we need to find work. That's the one thing we don't have. And once we find work, I can plug it in here and solve for that internal energy. So let's go ahead and solve for work. Work then is equal to negative P delta V. I better get a negative one is all I have to say. Negative, my pressure is 1 atm, right there. And then my volume is 4.5 e to the 6th minus 4 e to the 6th. And when I do that math, I get a work of negative 5 E5 liter atmospheres, don't forget. So that's my work. Can I plug in liter atmospheres and add that to joules? No. That would be a no. So I'm going to go ahead and solve for a conversion there. So negative 5 e to the 5 liter atmospheres, latums. I'm going to 101.325 or just 101.3 because that's what's on the sheet, joules for 1 latum. When I do that math, that gives me a work of negative 5.065 times 10 to the 7th joules. So that is in actuality what I am going to plug into the equation to solve. So when I do that, and just because you guys can do the math on your own, I take this, plug it in there, and add it to that joules. My final answer ends out being an internal energy of 7.94 times 10 to the 7th joules. And that's my answer. All right, that's it for this lecture. Talk to y'all next time for some very, very exciting enthalpy. See you soon.